let's talk a little bit about finding our zeros by factoring. And basically, we're going to be doing some practice of stuff that you've done in the past. This factoring, really, you should know how to do. If you are totally lost on this as we go over it, then you need to come get some extra help. Okay? Now, if we want to find the zeros by factoring, let's stop the conversation and listen. If we want to find the zeros by factoring, again, what we do to find zeros is we set the function equal to 0. Okay? So we set the function equal to 0, and how would we factor this? What do we look for first anytime we're factoring?
GCF.
Always look for a greatest common factor first. Okay? If you'll get into that habit, that'll greatly make your life easier. All right? Here we have a greatest common factor of x. So I can factor that out, and I've got an x squared plus 5x minus 6. Okay? So now, how do we factor the x squared plus 5x minus 6?
1 is x plus and 1 is x minus.
Okay, good. We see here, think about where it came from. When we're trying to factor, we're trying to undo a foiling, right? Okay? Well, the only things we could multiply to get the x squared would be x and x. We're not going to put x squared in 1. All right? So we're going to do x and x. And then look, since this is a minus 6, that's a product of the lasts, right, in foiling. So that's from our lasts. So my lasts, in order to get a negative, they have to have opposite signs. Okay? Otherwise, I'm going to get a positive 6 at the end. Okay? So if I want a 5 in the middle, I need to think, all right, I got that from multiplying one of the factors of 6 with one of the factors of 1. Okay? So this one's kind of nice. We just have a 1 in the front. But now I need to think what factors of 6 will combine to give me 5, the 6 and the 1. Okay? So I've got to do a plus 6 and a minus 1. Plus 6 minus 1 will give me my plus 5 in the middle. Okay? So, you are using factors of the negative 6 to get a positive 5 in the middle. Alright? So now, what are our zeros?
0, negative 6, and positive 5.
Very good. Okay? So given this, I can now sketch what this is going to look like. I have a 0 at 0. I have a 0 at 1. And 1, 2, 3, 4, 5, 6. I have a 0 at negative 6. Okay? What's the right side going to do?
Go up.
Go up. What's the left side going to do?
Go down.
Go down. So now I just need to fill in the middle. Okay? And notice all of those, they're just going straight through the zeros, because those are all just multiplicity of 1. Okay? Okay. Now, this next one has 4 terms. So how are we going to factor that? What strategy do we need to use? Rachel? Okay. Do you guys remember what we call that?
Grouping.
No, grouping. Grouping. Okay. Grouping the square. Not quite. Alright, so we're going to group these together. Alright? And we're going to take out a common factor from each group and then keep going, all right? See if you can figure that out on your own here. All right, so we got our 2 groups. And by the way, you can group these in a variety of ways. I could have grouped the 3x cubed with the minus 4x, and the negative 12x squared with the plus 16. Okay? The only way you couldn't group this is like to put the x cubed with the 16. Alright? But since I've got it here in this order already, what would be our common factor with 3x cubed and 12x squared?
3x squared.
Yeah, there's a 3x squared in common, and that leaves an x minus 4 in the parentheses, right? And then as I look at the last two terms, what would be the common factor there? We could do 4 or we could do negative 4, okay? And one little tip here is anytime that the first of the two is negative, go ahead and take it out with the common factor. So since that's a minus 4x, I'm going to take out the minus 4, and that's going to give me an x minus 4 in the parentheses, okay? If I had just taken out a positive 4, notice I would have gotten a minus x plus 4, and our two parentheses wouldn't match then, okay? The key on this is to get two sets of parentheses that match. Alright, so I've got to take out, so I've got to take out the negative with it. Okay? So I'm going to take out a negative 4, that'll make that a positive x, and a minus 4 there. Okay? So at this point, this set of parentheses and this set of parentheses are identical. Okay? Does everyone understand what we've done so far? Okay? So now, I'm going to take that out as a common factor. So I have an x minus 4 as my common factor here. And then what's left over is the 3x squared and the minus 4 that was there.
Do we have to put the x minus 4 squared, or no, we're just counting it as 1?
It's just 1. It's just like when you took out a 4 from both the 4 and the 16, you didn't make it a 4 squared. You were just factoring it out. Okay? So there's only one of them there. It's if you think about it like this, you know, if I were to distribute this set of parentheses back, I would distribute it to the 3x squared and to the minus 4. Right? Okay. So at this point, we can identify our zeros. Alright? I'm trying to get zeros, so this whole thing is equal to 0. So x would equal, what's the easy one? 4. Okay? But then I also have, what would make 3x squared minus 4 equal to 0?
2 over squared.
Okay? 2 over radical 3. If I add 4, I divide by 3, I get 4/3, and then I would have to square root. So x would be 2 over the square root of 3, and wait, what were we going to say, Han?
Plus or minus.
Perfect. Plus or minus. Don't forget, when you have radicals, if you square root both sides of an equation, you've got to use the positive or the negative one. Okay? And then to rationalize this, let's make that plus or minus 2 root 3 over 3. Okay? So we have 4, positive 2 root 3 over 3, and negative 2 root 3 over 3. Okay? And it makes sense that there are 3 zeros because our degree was 3. Okay? Now, if we were trying to graph this, okay, if we're trying to graph this, all of these have a multiplicity of 1, okay? So we would have 4, 1, 2, 3, 4. And then 2 root 3 over 3. Root 3 is about 1.7, so that'd be about 3.4 over 3. So that'd be about 1.1, 1.15. Okay? So there would be positive 2 root 3 over 3. And then here would be a negative 2 root 3 over 3. Okay? What's the right-hand side doing?
Up.
Going up. What's the left-hand side doing?
Down.
Going down. What's one other point I can really easily find just by looking at the original problem?
16, y-intercept.
The y-intercept is up here at 16, yeah. That can help you catch yourself on some of these little mistakes too. So I know it's going to go up here all the way up. That may or may not be the max, I don't know. But it's at least going to hit that 0, 16, come down, hit my other two zeros, and then end up going back up. Okay? So that's a rough idea of what that graph would look like.
How do you know the, I forgot what it's called, multiplicity.
The multiplicity?
How do you know that again?
Well, notice if there were multiplicity, I would have like the x minus 4 would be squared. Or when I solved it, it would have been 2 root 3 and 2 root 3, not the plus or minus. Okay? Alright, so we've been talking a little bit about multiplicity. We are going to do more with factoring, figuring out how to deal with ones that maybe we can't factor just by looking at it. Okay? But let's talk about these repeated zeros. This is something we've already mentioned, but I just want to make sure that you understand. And I want to start with the parent functions that we already know. Okay? Here we have the quadratic parent function, f of x equals x squared. And if you let that equal 0, then 0 would be your 0. Okay? But it would be a double root. Okay? So notice x equals 0 has a multiplicity of 2.
Why?
Okay? Well, because this is a quadratic. We got to have two answers if we set it equal to 0. Okay? So it has a multiplicity of 2, but think about your parent function. It came down, hit the 0, and then bounced back, like we mentioned earlier. Okay? Think about your cubic parent function. 0 is also the 0 here, but it has a multiplicity of 3. And again, like we mentioned when we were going over that homework, notice it comes up to the 0, levels off a little bit, and then continues to go up. Okay? So that's what happens when you have a multiplicity of 3. And the general rule is this. You see it up here at the top. If k is odd, the graph is going to cross through the x-axis at that point. Even if it's multiplicity of 5 or 7 or 9, okay? How high it is just determines how much we kind of level it off. Okay? So like a cube root might look like this. A fifth root might look like this. Okay? If it had a multiplicity of 5. If it had a multiplicity of like 9, it would level off even more. You know, we'd be really, really close for quite a while. Okay? But no matter how high it is, if it's odd, it's going to go through the x-axis. Okay? If the multiplicity is even, it is simply going to touch the axis and bounce back. Alright? Again, if we had, say, multiplicity 4, it's just going to level off a little bit more as it approaches that 0. Okay?
So the higher the multiplicity, the more level.
Exactly. The more it's going to level off. Alright? So here's a little example. What are our zeros in this case?
0 multiplicity 2.
Okay, 0 has a multiplicity of 2. Okay, what's another 0, somebody?
2.
2.
Negative 3.
Does 2 have multiplicity?
No.
No.
3 very happy.
Okay. -3 has it.
Oh, negative 3.
And good, it has a multiplicity of 3. Okay? So if I'm sketching this, if I'm trying to draw this graph, I put my zeros on here. There's 0, 2, and -1, 2, 3. I look at my end behavior, so the right side is going to do what? Go up. The left side is going to,
Down.
what's our degree here?
Go up.
Go down, it's odd.
Down.
X squared, x, and x cubed, right? So we have a total of x to the 6th. Okay?
Go up.
If you count your multiplicities, 3 plus 1 plus 2, we've got 6. So my left side is going to do the same thing that my right side is doing. Alright, it's going to go up. Okay?
Doesn't that have to like level off or something?
Yeah, so here, now we can look at our multiplicities. Alright? As we go to -3, you see it's leveling off a little bit here, but it is going to go through. Okay? As we approach 0, it's going to level off, and it's going to bounce back. Okay? Mm-hmm. And then finally, as we go to 2, it just has a multiplicity of 1, so we're going straight through that value. Okay? So, there's a sketch. There's a sketch of our graph. Okay? So one last thing I want to mention here. This is just a property of functions I want you to be aware of. Okay? This intermediate value theorem. We don't do a lot of real in-depth theory. It's more application and stuff. But I do want you to be familiar with this. The intermediate value theorem says this. It says, let A and B be real numbers such that A is less than B. If f is a polynomial function such that f of A does not equal f of B. Okay, so let's think about this and illustrate it so far. All right. So we've got this polynomial function. We don't know what it looks like exactly, but there's a polynomial function. And let's say, here's A, okay, which means this right here would be f of A, right? Mm-hmm. And then we also have a point over here. Let's say this is B. Okay, so this point, that means here we have f of B. All right, notice f of A does not equal f of B. It could be greater than, it could be less than, as long as it's not the same. That's all we care about. Okay? Now, let's see what this says. It says, in the interval, the closed interval AB, f takes on every value between f of A and f of B. Okay? Now, it may take on other values, but let's look at this. Let's highlight what we're talking about. Okay? Here are all the values. Let me use a smaller pen here. Okay? Here are all the values between f of A and f of B. Okay? So, in the interval that I'm dealing with, okay, which is, whoop, not there. It's from here to here, from A to B. you'll notice if I kind of box this in, you'll notice that on my graph, every value of the function between f of a and f of b is accounted for. The function equals everything in between those two. Now, in this example, there are some values that are lower than f of a that it also equals, okay? But we don't know exactly what those are. What we do know is that it will equal everything between f of a and f of b. So, let's put this into some understanding. Let's say that we have the point, let's say this is the point, 2, 8, and this point up here, point b, f of b, is the point 7, 15, okay? What this says, what the intermediate value theorem says, is that you could pick any number between 8 and 15, and we could find a point on our graph that will hit that value. Okay? So someone give me a value between 8 and 15.
9.
9, okay? So, if I look here for 9, let's say this is 9 right there. Okay? If I come straight across here, I will hit the function somewhere between 2 and 7. Okay? That's all this theorem is telling us. I am guaranteed to hit the function somewhere between 2 and 7. Okay? And you could pick any value between 8 and 15, and we will definitely hit it somewhere between 2 and 7.
94.
Okay? 94 is not between 8 and 15.
Guess that was what I'm looking for.
Okay? So, that would not be an intermediate value. Intermediate means between, okay? So, it has to be between the 8 and the 15, and we will find a point somewhere between 2 and 7 that hits that value. Okay? What property of polynomial functions is this a result of? All polynomial functions are
A result of
Oh, they're
ugly, annoying, hard to do.
Come on.
Oh, suck.
Get the brain in gear rather than the mouth. All right? Think. What's the property that we have here of all polynomial functions?
They're graphable.
They are graphable. What do we know about their graph?
They're
Ugly.
What's the domain of their graph?
Oh, all real numbers.
All real numbers. And beyond that even, it's not just all real numbers, but the function is also
Multiply. Multiplicity. Contraceptive.
continuous. All right? Okay, continuous. The only way we could get from 8 up to 15, if it's continuous, is we've got to cover the whole ground between 8 and 15. We're not allowed to jump from 8 up to like 10 and then go to 15. Otherwise it wouldn't be continuous. All right? So, that's our intermediate value theorem. Because it's continuous, if I have two values, if I have 2 points on a polynomial function, if I pick any value between the two y coordinates, I know that some x value will give me that. Okay? So, there you have it. That's the intermediate value theorem.